Good morning or good day. Thank you all for showing up. I got Anthony and George and Ignore and Jason, Marson. Good to see you all here and a handful of others. Uh, Today I want to talk about accelerated life testing more from the level of, well, there's a lot of different ways to do accelerated life testing, and let's figure out what's the right approach to do that. And before I move off of this screen, a few of you have already discovered the chat window. We'll be using that throughout, and please use that. And occasionally you'll see a questions tab. If you have a question, go ahead and put it in there. And my intention is to uh, um, hear from you regularly through the presentation. It's more like a discussion is my intent. But on the right side of your screen, you should see a download segment. Those you can highlight the slide set or a paper that I presented at RAMS in 2012 on the same topic. It has a bit more detail than what we'll go into today. But then there's also a set of links down on the right side, and we'll come back to those downloads and link screens near the end of the presentation also. So if you don't get a chance to click on all of those, we'll come right back to them. This is an ongoing webinar series, and I'm using the banner Accendo Reliability because I'm launching a website that has the recordings for these, plus a variety of other bits of information there. And hopefully you'll get a chance to check that out. The link is on the bottom of the links tab on the right. So got a handful more people dialing in, it looks like. I'm glad to see a good crowd today. Appreciate that. And just as a quick sound check, am I broadcasting all right? Have got everything off of mute and everything? So I got George's typing. Sounds good. Thanks, Anthony, George. All right. Yeah, the last couple of attempts at this process, I didn't quite get the sound right. So now I'll keep my fingers crossed and hope the slides also move along. All right. So many of you know that accelerated life test is a tool in our toolbox as reliability engineers to create an estimate of how long something will last. And there's more than one way to do this. There's lots of books published, and one of my favorites is by Wayne Nelson called Accelerated Testing. And he goes into depth from more of a statistician's point of view with a touch of engineering of how do you design and build these things. Bill Meeker and Luis Escobar also have a book out that goes a bit more into the statistics side of things, and they use some modern tools like S, I think is in the book, which today is R, our software packages that are available. ReliSoft has a variety of tools that are available, as do other vendors and so on. But most people tend to talk about the statistics of accelerated life testing, but that's not the whole story. So we'll explore a couple other pieces of accelerated testing today. And as I mentioned, there's my banner, Accelerated Accendo Reliability. One of the things we just kicked off of this, and this is why I added this banner, is a Dare to Know series of interviews with thought leaders. And I think we're up to like 7 or 8 now recorded. I got 2 more being recorded this week or in the next couple of weeks. Along with Tim Rogers, we're interviewing book publishers, blog authors. We hope to get some business leaders, some professional or some professors from different university programs to talk about their views on reliability primarily, and also then promote their book and things like that. So it's like a radio talk show interview, but our intention is to go after the thought leaders in our profession. So check out Accendo Reliability for those interviews. So some years ago, now longer than I'd like to admit, my boss, I was a manufacturing engineer in a factory, and we made heating cables, and my boss walked in and said, we have this new product, and he held out a sample of it, and he said, we need to know how long it'll last. And he says, I want you to figure that out. And so this is a piece of polymer that's been, some carbon black has been added to it. So it had this kind of self-regulating heating function in it. And we made it like a cable. Think of it as an electrical cable with two wires embedded in this polymer that had this special heating property, and then a jacket and insulation around the outside. And he explained that they were going to put this in concrete in bridges, and they needed to make sure that it lasted at least 20 years. And so I asked a bunch of questions, and I thought, well, this is great. I'm going to get to go to Italy where they were going to put these in bridges and watch them install it, and then hang out in a nearby chateau for 20 years and see how long they actually last. I had no idea that you could cheat time that way, and much less figure out how to estimate the life of something in less than the actual time. And so he kind of quickly realized that I had this dream going, and so he corrected me on that and told me to get back to work. And so it was my first brush with this question, and it was a clear customer expectation. It was in the contract, basically. They wanted us to show that it would last long enough. They didn't want to go through the expense of installing it until they knew it would be there long enough. As you can imagine, tearing up a concrete bridge to take out a heating cable and replace it is going to be really expensive. So they wanted it to last sufficiently long in order to justify the expense of the purchase. Now, one of the benefits of being a reliability engineer is that everything fails. Eventually, our sun is going to burn out. It has a lifetime. Don't like to think about that too often, but I also I don't like to think about my car wearing out, and it will eventually. And folks like us all around the world work with these customer expectations to understand what it is in some cases, and also to understand how to show that our product or our system or our production facility has some durability, will last long enough. Now, we also use this kind of information to make financial estimates. What is our warranty expenses going to be? Years ago, while I was at Hewlett Packard, we did a study of what was the biggest reason that a division missed their numbers. What made the biggest difference? And at the time, the CEO was very keen on, as she said, make the numbers. And she got upset with divisions that had too much profit or too little profit. Either way was not a good situation. So when we suspected that warranty was a big part of this, so we looked at the 45 or so divisions that were in the company and looked at their warranty numbers and looked at their financial reports. And if either was the number one or number two reason for the variability in actually estimating your numbers. You introduce a new product, it's usually with a wish and a prayer that it's reliable enough, but somebody has to make an estimate for the warranty accruals for the set-asides. And same thing we do in factories is what's our maintenance budget? How many spares do we need? Things like that. Well, that comes down to real numbers at the end of the day. And if we estimate it wrong, then at the end of the quarter, we tend to make an adjustment. And it can take money out of profit or it can put money back into profit. And it became clear to us that the ability for us to predict reliability for new products especially was essential for us from a financial point of view in order to make all of our numbers. So it became pretty critical for us to understand how to do this. And it may be the same picture in your organization. But most importantly, the reason we do accelerated testing is to make decisions. A lot of what we do as a reliability engineer is to make decisions. We don't just run tests and spend all that money and consume prototypes just because it's fun, even though it is. We do it because somebody wants to answer that question, will it last long enough? How long will it last? Will it meet the customer's expectations? The other reasons is we could be comparing two different designs or two different vendors or two different construction methods or whatever. And it's tied to a decision. So the rationale for doing accelerated life testing should always come down to it's making a decision. And that becomes one of the key factors in how we set up and design an accelerated test. Now that's completely different from the statistics, but it's really the first stop or first gate I recommend you consider when you're looking at doing a test. Well, who needs the information to make what decision? And then that test and the results should impact that decision in a meaningful way, should give them sufficient information to make a good decision. And that should be obvious, but I've seen it done so many times where the test is just run and nobody is really using it. And it seems like a waste of resources to me. So, I mean, do you need to know the lifetime of your products? We've got the chat windows open here. I mean, is this, and I think this might be an obvious question since you're attending a talk about accelerated life test, but do you need to know the distribution? And is it connected? I should add the question, is it connected to decisions in your organization? So Anthony, just like that example I had, is that it really is tied to warranty good. Yeah, maintenance requirements. Yeah, the hard part, George, is as the systems are getting older and older, as you know, it's hard to justify increasing number of spares. But if you can predict it and hit those numbers, then you're in pretty good shape. Yeah, yeah, and minimum lifetime susceptible. Yeah, Michael, I've run into that a lot of times, especially when you're really constrained on sample size and time. You can hit certain thresholds, but there's certain caveats to that, and we'll talk about some of those. Yeah, yeah, I'm running into more and more customers that are demanding, and it's a British standard. I think out of the Ministry of Defense, where a customer expects you to provide a reliability case. Think of it by analogy, a legal case. What's your rationale and logic for justifying that you've met the claims of the reliability claims or reliability specifications? So instead of saying thou shalt do FMEA and HALT testing and these particular demonstration tests, the British military is now going to their vendors saying, show me your logic and understanding of your product such that you can convince me a reasonable, rational argument that the reliability is adequate. So that turns the onus back to the supplier, as it always has been, to provide a bit of information about how they know. And so it becomes pretty critical as we think through how long something should last. So accelerated life test, and there's so many. Yeah, V1, V5, those are hard to get. That's that early tail of the distribution, John. So we'll talk about how to get some of those things from these different approaches. But it's something that we all face as we need to know this for a variety of different reasons. Well, accelerated life testing has been around for quite a while. It's a convenient way to cheat time and to compress time, or to alter the results such that we get a meaningful result. So some years ago, I asked Wayne Nelson, who I've known right from that very first project. He was very helpful when I first bought his book. I met him at a conference This is more than 20 years ago now. And we've stayed in touch over the years, but a couple of years ago, I asked him, how do you design the perfect accelerated life test? And he says, oh, that's easy. And he says, all you have to do is ship all of your products to your customers and keep track of them and do failure analysis when they fail and track how long each one lasts. And then you have the information you need to create a test. He says, you need to know what fails. You need to know what stresses are applied that are meaningful for your customer's environment. And you need to know how your technology reacts to the stresses that your customers are causing or creating around your product. And I thought, well, that's not very helpful. He says, well, you asked for the perfect accelerated life test. Now, everything we do short of that, we're making assumptions and we're making engineering judgment and we're making guesses. We're taking risks and we're being judicious in how we do that. We use a lot of science and engineering to do it, but short of letting it go to our customers, we don't really know. There's some uncertainty about this. I countered with another way to do it is instead of giving it to your customers, do it yourself in the lab. And he countered, says, no, your customers will use different stresses and different loadings, and they have different expectations. Remember that the customer defines the failure. So even just replicating what customers do in our lab isn't always the appropriate way to evaluate our products. It's that balance between what we really need to know and what we're capable of finding out. So I'm going to go through just a couple of the different types of accelerated tests that are out there. There's lots and lots of different names for these in the literature. But it's just a rundown of 5 different basic approaches. And the 6th one is obviously just let your customers do it. I tend to call that the Microsoft method, but that's not recommended if you really need to know how long something will last before your customers tell you. One of them is time compression. And this one's intuitive. If the classic example is a car door. If the engineers for a new vehicle, a new hinge, estimate that the customers will open and close a car door, say 10,000 times over 5 years. And I'm just making those numbers up. I don't know what they really are. They may get a robot or they get a couple of interns or folks available to open and close the doors and do it 10,000 times and periodically measure the amount of resistance, the different parameters for actually closing it. You could measure wear patterns and rate of wear. You could do all kinds of things to simulate 5 years just by doing it more often. Now, this only works if the product's not used 24/7. If your product is like a server that's running in the backbone of eBay's system, and it's running hard 24 hours a day, 7 days a week, well, there's no room there for time compression. So this really works in some circumstances when you have something that's used periodically and you can accelerate it in a meaningful way. The caveat is, I heard the story about these guys wanted to test a new design for a toaster, and they hired a couple of interns to make toast all day long. And so what they did is they put some, your mileage may vary actually, is a nichrome wire type of a system, and there's the side of the toaster, and there is a bead of some kind of high temperature solder or weld, and then the nichrome wire. And if you look inside the toaster, they usually have this zigzag pattern of some sort. And so they put in a piece of bread, and they were being told that they had to replicate making a family of 4's expected load of toast per day for a year and see how it worked. And so they thought, well, we just make these as quick as we can. And so they put it in there and they heated this wire up, and it would flex just slightly. I'll just draw a line like this. As it heated up, it expanded and it flexed right at this joint. And that's right where they expected the failures to occur. But as soon as it finished one cycle, they started another cycle. So this wire pretty much stayed hot and stayed up here. So they didn't get the flexing back and forth that would cause this metal fatigue at the joint. So time compression also comes with the caveat is that it's got to replicate the stresses at the failure mechanism level. And it's a pretty simple formula. The math for this is trivial. It's the number of cycles I do in testing versus the number of cycles in use. That's my acceleration factor. But it only works if I can recreate the failure mechanisms that I would get normally. Now, things that are difficult, like the car door, is what about dust and debris and leaves and oils and greases and oxidation and all the other phenomena that take time to occur versus just opening and closing the door. So it does take a little bit of engineering to think through, how does this thing really fail? And that's very, very true for any approach in accelerated testing. What's the failure mechanism? So time compression is one way, and it's suitable in many cases if you can actually use your product more often than your customer does in a meaningful way. That makes it work. Another one is, well, you're going to have to build your own model. I don't have a formula. Nobody's studied this before. Maybe it's a new technology or it's a brand new mechanical device. And so what I do is I sort out what's the highest level of stress that I can apply to this thing and how long before it fails. And so I might be testing it to the equivalent of 1 year of time at a high stress. At a moderate stress, say I get 2.5 years equivalent, and at the lowest stress, where you pick this value such that you'll get some failures before you have to finish off the testing, and let's say it gives me 4, but in my use condition, I may be out at a longer period of time. Now the idea is that there's a pretty standard formula, is you put a ratio of 4 to 2 to 1 samples here, and ideally you have at least 5 samples in the highest stress, and you go until you have at least 5 failures in each level. And then basically what I'm doing is going to plot the distribution at each of these times, the time to failure distributions, and project that back to my use conditions. And I can, depending on how that behaves, and obviously having some understanding of your failure mechanism will help you know what formula to use, but it might be a power law formula, it might be an inverse squared formula. It may have some different function, but it allows you to create your own model, create your own distribution. And as John talked about, if I'm interested in the B1 or B5, the first percentile or fifth percentile, I have the distribution. And I can then say that my B1 is going to be at 5 years, for example, in this simple example. But the idea is that this takes a bunch of samples. If I need at least 5 failures, that's 5, 10, and 20, if I'm doing my math correctly in my head. So that may or may not be possible depending on your product. Now, keeping in mind that this is generally done on a single failure mechanism. So it might be just on a bearing, it might be just on a flange or a hinge, it might be just on a paint coating, generally not the entire product. Inside an entire product, we have so many different failure mechanisms that I may evoke different failure mechanisms at the highest stress than here, and then this model falls apart. We really need to have the same failures from the same failure mechanism throughout. So let's build a model. It's expensive. It's when I don't have other information available. I don't have prior information. I don't have failure mechanism details. I don't have a lot of information. And this can be very expensive to do. I did one years ago for just a solder joint. and it costs us about $100,000 to make the test boards, to set up the chambers, the monitoring equipment, and so on. So don't do this one unless it's really important, worth the cost of doing it. So another method is you already have the model. Either you did the previous work on that other one, or you have a failure mechanism that's been well studied. Solder joints have the Norris-Landsberg equation. Peck's equation looks at humidity and temperature, and it's for plastic encapsulated ASICs and components, essentially. And it looks for defects in the encapsulant causing corrosion internal to the product. It also is a pretty good set of stresses for looking at electronics for electromigration and for contamination issues. So this basic model then applies for a range of different failure mechanisms, but its primary thing is looking at encapsulant, the ability of the encapsulants to seal. But that's how specific you need to be, is in the literature, drawing a blank, they just changed their names. It used to be the Reliability Information Action Center, RIAC. They just got reorganized and they've got a new name, but they have a model or a site called WARP, WARP, which lists literally hundreds of different formulas, and it's based on physics of failure models for specific failure mechanisms. So it's a good place to go look if you've got a particular type of material or a particular kind of component. There's a lot of the fundamental knowledge is there to create these formulas. And what this does is it allows me to test, instead of, as in the previous slide, instead of testing multiple stresses, I'm able to test just one stress. And I can pick, say, a modestly high stress, and then apply that model, which provides me an acceleration factor. If I can get my cursor to work, to translate that single test experience back to my use test. But that only works if I've got a model that gives me this acceleration factor. The danger is that if that model is not appropriate for your failure mechanism, then this activation energy and this exponent here may not be appropriate. So it's with due caution that you're getting the right failures. And so again, with any failure, with any of these tests, it's really focusing on the failure mechanisms and making sure you get the right ones in your testing. Now, you certainly can be surprised. George, it is WARP, WARP. Don't even remember what it stands for, but it's a pretty nice collection of papers that deal with all the models. So anyway, that's one way to go. And it does save you time if you're willing to take the risk that your failure mechanisms that you actually see are appropriate for that model. So it's another step away from actually letting your customers drive them to failure. Another use of these models is called a step stress. In some cases, and this really only applies when you have accumulated damage, is that I can apply a modest amount of stress for some finite amount of time, say a week, and it accumulates damage slowly. And if it fails at that point, it's a really strong indicator that I've got a short failure or short time to failure according to my acceleration model. But in order to get results quicker, I increase the stress, and I might run it at say a higher temperature for a week. It's accumulating damage according to a model quicker. And so it's a balance between just using one stress and hoping for the best, where if I use a step stress, I can use the mathematics behind it to determine if my model is appropriate or not. Where if I use a single point of stress and run to failure and do that, I'm losing some of the diagnostics capability. Step stress also can be faster in some cases. The danger is that if you get too too high of a stress, you may cause other failure mechanisms to occur. The simple example is if I keep increasing temperature, eventually I'm going to cross a phase transition and melt something. So then that failure mechanism may not apply. It's a similar concept we use in halt testing, where we use multiple stresses in those cases so that de-evolving the results back to a prediction is more difficult. Step stress relies on having a good model, having a range of steps that are going to cause accumulated damage. And so it's got limited application, but it is a convenient approach when those conditions apply. And then one more is degradation. Oh, thanks, Merson. This is again dependent on the failure mechanism. If the failure mechanism erodes or degrades something you can measure, say the very first test I did on a heating cable is we could measure the resistivity of the cable, and the resistivity would decrease over time. And we knew it was due to oxidation. It was a chemical process, so we used the Arrhenius equation to monitor that effective temperature on the performance of the resistivity, and we can measure it periodically and track it going straight down. I also have used this with products that had wear. It was a medical device that was sliding a probe basically along a cylinder, and it would wear. And if it got too thin, it was dangerous at that point, so that we wanted to find out what the rate of wear was. So we would cycle it 100 times and then go measure it, and then cycle it 100 times and go measure it. And it gave us a plot of cycles per wear versus wear. So if the failure mechanism gives you a monotonic performance, either decrease or increase, something that would go towards a failure, then that's a degradation model. Now, the advantage of this is it usually takes very few samples. If I'm doing that build a model type system, I'm going to need 50 to 100 samples, ideally, to make that work. Whereas if the failure mechanism has a nice degradation path and it doesn't heal itself, it doesn't get better with time or worse, and doesn't vary, it just gets worse, I could probably do the test with 15 to 20 samples. And really, when you're pushed, you could go even fewer. But it's a convenient way if the failure mechanism fits into this model. So those are 5 different basic approaches. I can compress time, I can build a model, I can use a model, I can do step stress, and I can use degradation. Each one, to some extent, to a major extent, I should say, relies on the failure mechanism. And you're right, John. Step stress is what we use in halt testing. It helps us find the margins and find the point between functional and not functional. And it's pretty classic. When I tie that to a good model of the failure mechanism where I'm accumulating damage, then I can project out and use an acceleration factor at each stress level, and then mathematically add those together to get my prediction of how long something will last. So I probably mentioned failure mechanism a bit too many times, but the idea is over time, this is a Weibull plot of a cumulative distribution function. So I have time and then the probability of failure, a cumulative probability of failure. So I have a relatively low failure point at 1 year and out to 4 years. It's a fraction of a percent of failures. And this is on a very crude portion of a log plot or a log plot. But let's say I have another failure mechanism that shows up just after 4 years of use. And it's completely masked and has very low probability of occurring early on. Maybe it's a accumulated damage type phenomena that just takes time before it appears and then takes off. So one of the hazards with any of our reliability predictions from accelerated testing is this phenomena where either I cause a different failure mechanism to occur, or I'm masking it by a different failure mechanism that has a higher probability of occurring at shorter time intervals. And so part of the overall judgment is, well, how long do I run the test? How long do I simulate the stresses for? And very, very particular about what failure mechanism am I trying to excite or evolve. So the tools like FMEA and HALT testing and engineering judgment and risk analysis, hazard analysis, all of those come into play to sort out what we need to look for and what we need to monitor. And that's the entry point in going into accelerated testing is, well, what's the failure mechanism? And then that, coupled with the decision-making process, allows us to actually pick the appropriate model for this. So this is going to be more of a rhetorical question, is, I mean, hopefully for your dominant failure mechanisms, you have some model for it. And if you don't, use the information you're gathering about your failures to isolate those failure mechanisms and create those time to failure models. It greatly enhances your ability to determine whether or not the fixes you're making and the design changes you're making or the vendor changes and process changes are actually making a difference if you can use a model to help you design that test. All right, so a little bit about the selection criteria. So I think I've got 6 different criteria outlined in here, and it's like any decision-making processes. I've got multiple criteria basically to help me judge what's correct. Now, in some cases, I just need a result that's meaningful. So if I have a failure mechanism of wear, and I have a test design that doesn't actually cause any wear to occur, I just put it in an oven, say, let it run at temperature, the Arrhenius equation is not going to help me all day long. It doesn't relate to the failure mechanism. So the number one criteria for me is that the results actually reflect the failure mechanism and in a way that you can translate back to your customer's environment. So the other aspect of this is the confidence. I'm using a sample to make a projection about a population. If I only use 1 or 2 samples, I get information. I get information about what fails and when it fails, and that may be useful back to your design team to focus on what actually is failing. But if I want to know the reliability of something out to some lifetime, I also need to understand that there's a sampling problem, that my selection of prototypes that I use or samples I use for the testing may not be representative of the population. And so, I mean, we're already breaking some of the rules of regression, is we're going to use some very accelerated and early failures, and then we're going to project back to use conditions. We're going to extrapolate, which if you vaguely remember or even fully remember your undergraduate stats courses, because we're not supposed to do that. There's a lot of risk to that. Well, this confidence doesn't take that into account, but it sure can make it worse if you use very few samples. So it's a combination of sampling and the risk that we take with just creating a subset to project about the future. We also have the issues of extrapolation and regression models that we use, and we just have all the experimental error. So part of the design criteria for the test is, does it make sense? Can it actually tell us something useful about the failure mechanism over time? Yeah, exactly, George. Yeah, the statisticians cringe when they're looking at extrapolation, but it's a necessary evil for a lot of our models for reliability. We're projecting, if nothing else, we're projecting out to the future what we expect is going to happen. Another one is measures. Can we actually measure what we're trying to that's directly related to the failure mechanism? That heating cable example is I was measuring resistivity, which was a surrogate for the power output of this thing, how much heat would actually be generated by the cable. Ideally, I would power it up and measure its heat, but that was a much more difficult and costly measurement, whereas measuring resistivity was shown to be related, so it was a surrogate. So if I can't measure what I'm actually interested in, if it's unrelated to the actual results, it might be the color of the cable, if that's the only thing I can measure, then I don't have a test here. If the style of testing I'm doing is inappropriate. But there's some threshold of some surrogate or model. I'm taking some risk that what I measure is related to the failure mechanism, and that there's not too much additional noise. There's some threshold there that says that's good enough. And ideally, if I can measure the actual failure mechanism directly, that's best. So the idea is that for each of these criteria is that I can set up a ranking basically of what's appropriate, and then judge each of the different approaches against these different means of doing it. Cost. You can't tell me that cost isn't a factor in setting up an accelerated life test. It takes personnel and resources and space and those expensive prototypes. And then it also takes time. So the cost, if I'm doing a degradation model with the fewest number of samples, that may be the lowest cost. Whereas if I'm building a new model, that may take an immense amount of cost. So that's one way to separate out these different approaches. The cost is always balanced by how important it is to get to the answer. Now, in the paper that I mentioned at the start, and I'll bring the link back up here as we finish, they also define precision, duration, and samples. One of them that's buried in here is that I get it on time. Is the duration of the test, it's probably the most direct to it, is tied to that somebody's got to make a decision. So if my accelerated test runs for 6 months, but the development team or you need to choose a vendor, or you need to choose a technology in 3 months, I may not have sufficient information to help you make that decision. So I need to look for a test that runs faster. So maybe a step stress or some other style of accelerated testing that I could get the results quicker. But if I can't get the results in time, it's not all that useful. If I can't afford to run the test for the value of the information of it, then again, that's not an appropriate test. So each of these different approaches can be judged against these different 6 different criteria, and then you can use this kind of a decision model, or you can weight these at different factors, what's important to you and your organization. But the idea is it's not just about the statistics. It's not just the precision piece of this thing. It's also how realistic is it? Am I getting the right failure mechanisms that have a good relationship back to use conditions? Can I get samples? That's another similar to cost, but I don't know how. I've only had one test where they told me I could use as many samples as I wanted. It was on zip ties for holding cables on a solar panel array. One of the issues was that the ties that they were using to secure the cables were oxidizing and fracturing, and then the weight of the cables would pull the connectors apart and take a whole string offline. So they gave me, boxes full of these samples from 3 different vendors. I had thousands and thousands of samples, way more than I ever could use. So that's the one example, in my experience, of actually having too many samples. We were limited by the cost and how we measured it, because we were measuring tensile strength, and the cost of making the measurements and aging it was more of a criteria for us. So depending on your failure mechanisms and the different approaches that are viable, one or more of the different approaches may be obvious. Now, in some cases, there might be 2 or 3 different ways to do it, the testing with different setups. And then you can weight the different decision criteria to help you make a decision. But my intention with this discussion is to take a look at more than just the statistics and look at the different ways of doing accelerated testing and allow you to do some comparison. Yeah, it's George, it's an unusual, yeah. Yeah, exactly. And these things were underneath the panels. These and they had carbon black. That's why a lot of these zip ties that you see are black, is they're doped with a UV protection material to help them resist that. But when you expect it to last for 20 years, it's not going to work. Just oxidation in general is going to get to you eventually. And so overall, the idea here is that we have a lot of tools in the accelerated testing arena. They all have different costs, they have different strengths, they have different ways of making the measurements. Sometimes it's repeated measurements, sometimes it's accumulated damage, and we need to monitor something that's related to that. But in general, we start with the failure mechanism, and then we work out towards, well, how can I actually use the fewest number of assumptions at the lowest cost and get results in time for the decision makers to use it. That's the overall message here. Then you got to open the book up and figure out how to do the math, do the calculations. So I know I'm coming up near the end of my slides, I believe. But what criteria do you use? I listed a few here, talked about a couple of them. There's others in the paper. But how do you pick an accelerated life test? And please don't tell me you always use the same one. So how do you create accelerated life tests on a regular basis? And how do you pick which approach to use? And the reason I mention this, don't always use the same one, is that I've seen that a bit too many times, and where the testing, it was completely unrelated to the failure mechanism. Somebody had changed the fundamental materials, and the team was still using the same test that was based on the original materials, and they never failed it. They thought they had a good model and acceleration factor, but it had nothing to do with the materials they were using. And they were happily using all of those results that were essentially meaningless. So rethink every one of these tests. Yeah, mimic the use conditions as best you can. That's why the automakers still have test tracks, and they throw a couple of engineers in cars and drive them all over the place and run the air conditioner at full tilt at altitude in the winter in Colorado, and then run the heater at full tilt in Arizona in the summer. And they put them through their paces. It's not technically a accelerated test, but they are trying to replicate as close as possible the customer's use experience and force failures to occur. Now, John, one of the things that we've seen in a lot of organizations is creating an environmental test manual or an environmental manual. So what is the set of conditions in our customer's area? What can we do with that? Yeah, field data. Yeah, I often take the one of the early discussions with that heating cable is I wanted to go to customer sites that had been using a product for some period of time. So I wanted to create a model for an existing product that had been in the field for 10 years. But I wanted to verify the model actually replicated what customers did. So I wanted to get samples from the field and analyze them to see if their resistivity was as we would predict. And the marketing guys just would wouldn't hear of that. They wouldn't let me go talk to customers to go get samples for a life test. They didn't want us to talk about failures. They didn't want us to talk about degradation. They didn't want us to say that your product may not be as good as it was the day you put it in place. I never did win that battle. In other circumstances, we were able to get to it. Yeah, careful, Anthony, with the extreme conditions. There's a keep in mind that it's a balance for how many people are going to be using your product at the extreme conditions. It's a balance with, is your product robust? Because if it can survive the extreme conditions, it's often more likely it'll survive the nominal use conditions. Yeah. Yeah, George, they just guessed at the warranties. I mean, they thought they had a bunch of math and numbers, and they had this test that they were running, and then the warranties just showed up. The finance guys tended to adjust it based on actual patterns from the last couple of months, but they were completely in the dark when a new product came out. It took them a couple of months to sort it out. Hence that variability in their actual performance. So here's one to think about. So let's say in this, I don't know that there's actually a capacitor in this structure, but think of the electrical grid and those big can capacitors that sit out there along the lines, and they have a high voltage load. They're an outdoor pole-mounted piece of equipment, and the dominant failure mechanism is insulation breakdown. Is the dielectric material, which is between the plates of the foil of a large electrolytic capacitor, is a coating that voltage can eventually break down. It'll erode it and then punch a hole through it and create a short, thus losing the capacitance. So how would you test one of these things? We want it to survive on the pole for 20 years. It costs us a fortune to go out and replace these things with crews and safety and all the other aspects of it. So we're looking at a new vendor, and we want to run it through a test. Which test would you use? Or what questions would you need to answer in order to decide which test to run? Let's see, George is typing, but I'm quite sure many of you have had experience of setting up tasks. Now we have a failure mechanism. It's hard to measure. Yeah, what's the degradation rate of the insulation? It's more of a voltage mechanism, and it's a punch through. So it'll think of it as a very thin layer of deposited oxides that then the voltage corrodes or chips away. It's almost like a physical process. And then when you get a thin spot, the voltage goes up pretty high, and then it punches through. So it's one way that these things can happen. So it's hard to measure. It's very difficult to measure the parameters that change as that dielectric layer changes. Plus, it can get better. There's regenerative states, and there's usually dielectric solutions that help redeposit in certain circumstances the dielectric. So it's degradation method generally doesn't work. And also, the other one we can rule out is the time compression. These capacitors are operating as long as there's voltage across them, which is typically 24/7, except in my neighborhood last week. So time compression's not a viable one. So there are models available for insulation breakdown. Now we got to dive into, as George is getting at, is it a polymer based? Is it oxidative based? What's the construction? What's the actual chemistry of what's going on there? And maybe there's an existing model out there, and we could use the temperature and or voltage gradients to set up an appropriate test. So very quickly, it's just what's possible. Now I might have 2 or 3 different models available. Now which ones give us, with a little bit of planning, which ones give us the timeline and the cost parameters that we need to actually pick the right one? Yeah, very similar to oil breakdown, although like an oil breakdown, you have to take a sample out and measure it in some meaningful way. Whereas in the capacitor, we lose the capacitor itself if we take it apart. Um, so it becomes a destructive test if I'm doing a repeated measurement. So something like stress test may not be appropriate. So it's one to think through, right? And the only reason I brought up this example is to think through from the failure mechanism level, how would you go about doing this test? So there's a couple of areas here for criteria, and you can certainly add or subtract from that list and come up with other ones. But cost is always a constraint, but it's not the only one. I could do a very inexpensive test that has really no precision whatsoever. My plus or minus, my sampling error basically means that it's good from 0 to 100 years, and we're not sure what the real answer is. If ideally, get it as realistic as you can, get it as close to your actual customer use as you can. The balance is that oftentimes that involves multiple failure mechanisms, multiple stresses, and that can increase the cost. So these things are not independent of each other. Each of these different criteria will impact and influence the other ones, depending on which particular approach we can use. So start with the failure mechanism, rule out the ones that are just not feasible at all, not possible at all, and then start working down the criteria that are important for your organization. And the bottom line is will the results be meaningful for the decision makers that have to make decisions based on that information? If the test is not going to be used for a decision, I highly recommend you just don't bother running the test. What's the point? If the test is going to take 6 months, but you need an answer in 3 months, what's the trade-off? How do you get there faster? Can you push the stresses? Can we use a different approach? Can we use a surrogate, maybe a test vehicle that's not the entire product, so on? How can we get to answers when we need them? Right? And in rare cases, you'll have plenty of samples. Most of the time, we won't. Now, the different approaches, I just use a very high-level summary of these approaches. Each of these have many variations. Sometimes we have destructive testing. Sometimes we can use repeated measurements. Sometimes we can measure time to failure very accurately. Other times, it's very difficult to measure the time to failure. Each of these have different variations, and it gets into the details, which Wayne Nelson and others have written about extensively. So there's plenty of different models out there. But by narrowing it down to the type of model that you're looking for, it'll greatly improve your ability to design and build and execute a test that actually is useful for your organization and for your decision makers. So the last question for you to think about is, who should be involved in selecting the approach? And I suggest that it's not just the reliability engineer. It's not just a statistician. It's obviously the decision makers. It's the people that need the answers. And if we can't convince them that this approach is adequate to answer the question for them that they're trying to create a decision about, again, why are we doing the test? I can do a very sophisticated test, but if nobody understands it, that doesn't really help a whole lot. Thanks, Marcin. Yeah, I know I'm up against the hour here, so appreciate it. But in general, this is a picture of me testing some climbing gear. But basically, it's, what are the risks involved? And what's the appropriate test according to the criteria? I outlined a handful of them. There may be others. I'm sure there are. But what's the value? Is this test going to be tied to a decision, which is usually the biggest value you can find in running one of these tests? And then get into the details. How am I actually going to run this test? How am I going to collect the information? How am I going to analyze it? And then document it. Those are all basics for any of our types of tests. So I'm going to bring up the link for the Accendo Reliability, where you can, if you join that site, you can pick up a download of the Finding Value ebook. There's also one on reliability and maturity, which talks about assessing your organization. It's there. Plus the recording for this webinar and the past 6 or 7 of them are also there. So hope to see you out there. And I think, let me pull up the links for you. Yeah, on the right side is you can download the slides, and you can download the paper that's from a RAMS conference a couple of years ago, plus the link to the Accendo Reliability, where you can give me a couple of days to get the recording up there, but please share it with your friends, and you can see some of the past episodes or sessions that are up there, plus the Dare to Know interviews are also available for people that get registered with the site. So